Example number 2 asks us to find the maximum and minimum points and values, if they exist, for the function f of x equal to x squared plus 1 on the following intervals. So let's go ahead and get a graph of that guy. Okay, so f of x is equal to x squared plus 1. So you all know that that looks like a... We're just going to do this one out graphically here. We're not going to go through the proof for any of these values. Okay, so I just want you to get an idea of what minimums and maximums look like. Now, with open and closed intervals, you got to be a little bit careful. Okay, so you'll see in just a second why that's true. So x squared plus 1. Well, that's up at a height of 1. Squared function looks like a u. So it goes like this on this side. And then something like that on that side, right? Let's see if I can make it a little bit more symmetric. That wasn't even any better, was it? Okay, one more time, and that's it. Oh, man. I'm just horrible drawing on that side. Okay, anyway. So we've got this interval, negative infinity to infinity. So what we're saying is anywhere on the x-axis, where is the minimum point on the x-axis and where's the maximum? Well, there's clearly a minimum point here. Okay, and so we have a minimum at 0, 0, 1. Right, because this guy's up at a height of 1. So that's our minimum. The maximum, though, well, there is none. And the reason that there's no maximum is this guy keeps on increasing forever, and so does this guy. So there's never a point at which we can say, yep, the function has reached its highest point. Okay, so we say none for that. And that's it. That's all you got to do for A. Okay, for B, B says, let's take a look at the interval negative 1 to 1. Well, we still have, so that interval, I'm going to do it here in yellow. Okay, so there it is. Here's negative 1. Here's 1. Now, we're not including those endpoints, so we can't quite get to those ends. So we still have a minimum value at 0, 1, because all we're looking at is from here through here. That's all we're looking at. Now, if I'd have drawn this real symmetric here, we know that both these two end guys are at the same height, but here's the problem with that. We're not including the endpoints. So what we're saying is we can't go out to 1. We can just get super close to 1. So if you start talking about maximums, and you try to give me a maximum over here, let's say at 0.9. If I zoom in on the function, okay, the function cuts off at 1. So you give me 0.9. But if I go out to 0.99 and I get closer, I get higher. But I can always go to 0.99 and that'll get me even higher. And then 0.9999 and that'll get me even higher. The thing is, there's no limit to how many 0.9s I can put at the end here. So there's an infinite amount of points that are still above whichever value I think is the highest. So there is no maximum. And that works the same over here in this direction. So there's no maximum no matter what I look at. And then the reason for that is because the interval itself is open. If the interval is closed, then I can get to the end, and if I can get to the end, then I can find a minimum or a maximum. So when you have open intervals, you can have a minimum or a maximum, but it doesn't guarantee that you'll have a minimum or a maximum. When you have a closed interval, you'll always have a minimum or a maximum on a closed interval in which the function is defined over the entire interval. Now, if you've got like an asymptote or something like that, then you won't have a minimum or a maximum, even though it's on a closed interval. But we're talking about a continuous function on a closed interval, which this is clearly continuous. So C. Oh, I just did C. I'm sorry. That was C. Let's do B. Okay, so let's switch this guy right here to C. I was reading across, not up and down. And B is from 0 to infinity, but it's not including 0. So here's the thing. As I as I get closer and closer to 0, my values keep getting closer and closer to a height value of 1. But again, like let's say I go to 0.1. Well, I can get closer. I can get a lower value by going to, let's say, 0.01, and then 0.001, and then 0.0001. As soon as I keep pushing closer and closer, I keep getting smaller and smaller values. I'll never reach a height of 1 right here, but I'll get closer and closer. So no matter what you think is your minimum value, I can find a value that's just a little bit closer to 1 than what you can find. So there is no minimum. And that really is because this guy is an open interval. Now again, an open interval doesn't guarantee no minimum or no maximum, something like that. But if it's a continuous function, okay, and as we reach that side, that value would have been a minimum. So if 0 would have been a minimum, okay, then we probably have a good chance of not having a minimum on that. Now, is it possible to do it another way? Yeah, we can work around with piecewise defined functions. So that's not a hard rule, but it gives us some kind of justification. So min, there's none. Max, well, same idea applies. I go from 0 to infinity. So since I keep going out here in this direction forever, it keeps going up. There is no max. Okay, let's look at D. D is the closed interval, -1 to 1. Now this is interesting because now look at this interval. It's so close to this interval. The only difference is we're including the endpoints of the interval. Because we're doing that, here's -1, here's 1. On that interval, 0, our minimum is still 0, 1. However, we have a max at either 1 over 2 up or -1 over 2 up. There's no way to get any higher than 2 on that interval, but you can reach it. Okay, so we've found our min and max. So notice that this one only had a minimum. This guy had a minimum and a maximum because we had this closed interval. Okay, E. E is from 0 to 1. So not including 0. Over here to 1. So not including 0, I can get as close to this height as I want. Okay. I can keep coming down, but I'm never going to be able to reach 1. So I can keep getting closer and closer as much as I want. So there is no min. Now the maximum on the interval, yep, that guy's right here because we are including the value 1, and that maximum on the interval occurs at 1, 2. Because look at F. Well, for F, our interval is including 1/2 and up to 1. So here's a half, here's 1. We're including these guys, so clearly we have a minimum and we've got a maximum. Our minimum occurs at 1/2, comma 1 plus 1/2 squared, so that's 1 1/4 or 1.25, I believe. The maximum will occur at this end of the interval, which is at 1, and we plug that in, we get 2 out. For G, that is not including -2, but including 1. So let's go ahead and take a look at that. It's a little bit different. Now let's just redraw this guy here. So from -2 to +1, not including, including. At -2, we're clearly higher than at +1. So this is where we would like to have our maximum, but we never reach -2, so we can always just squeeze just a little bit higher, okay? So that gives us no max. So max, there is none. Now the minimum, well look, that contains this guy right here, which is at 0, so there is a minimum at 0, 1. And H. So including -2, not including 1 this time. Well, again, there's still a min, clearly at 0, 1. There's still a min because it's concluded on that interval. But now, we're including this, not including this. Since we're including this, we can get up to this point right here, which is our maximum. And so we do have a max for this guy, which occurs at -2. When we plug -2 in, we get a height value of 5 out.